Yeah? Oh, hello, hello. I heard I need to do my own timekeeping. I am Greek though, so might become an issue. Hi, I am Alexander Chatzizacharias. A little bit of a tricky last name, but you kind of get used to it after 33 years. I really like bouldering. I really like playing tabletop games like Dungeons & Dragons and Magic the Gathering. And my biggest hobby probably is video games. I really like playing video games. Any other gamers here? Good. Well, you are definitely at the right talk. I work at a company called J-Driven here in the Netherlands. And I work as a backend software engineer at the moment for rootscanner.com. And that was pretty much all I had to say about me. So I am a nerd that really gets distracted by shiny things. And roughly a year ago, ChatGPT started becoming big. And I was like, OK, well, this is shiny. I want to know more about this. So I was like, OK, how does this work? Well, a lot of things go into ChatGPT, so I couldn't really teach myself how to do everything. But there's one term that kept coming back, and that is vector databases. So I was like, OK, what is this thing? What are the vector databases? How can I use them? Can I use them? So I went on an exploration for myself. And when I go exploring new techs, I try to make games out of those new techs or games using that tech. And that is what I want to show you today. And hopefully you'll get inspired to use vector databases as well in your everyday work or in your hobby projects. And who knows, maybe you'll be somebody here will revolutionize our industry soon. All right. Before we get into vector databases, we have to start with something, well, fairly important, vectors. Are there any mathematicians here? Oh, now I have to be careful, huh? OK, so what are vectors? Vectors are a mathematical construct, and when you Google vectors, this is a little bit what you'll see. A letter, because math really likes letters for some reason, with an arrow on top of it. And vectors are, well, you can say they're a data structure that represent a length and a direction. Thankfully, we don't really care about the mathematical way of defining vectors and using vectors. So we can simplify this, and we can think of vectors as an array of numbers. And when you hear, OK, this vector has 2 dimensions, basically you can think for yourself, OK, it's an array of 2 numbers. If you hear, OK, this vector has 3 dimensions, it is basically an array of 3 numbers. And if it has 8 dimensions, it's an array of 8 numbers. Pretty simple, right? Now, vectors can go up into, well, 1,000 dimensions. So it can get pretty complicated. But what's really nice about vectors is they're a very convenient way to organize data. And typically in gaming, you keep hearing about vectors. They're extensively used as coordinate systems. And now, well, they're starting to be used outside of gaming and, well, in our everyday work. So how does software engineering use vectors, or more traditional software engineering? Let's say you have a piece of text like that. Then you vectorize it into something like this. So this is a vector representation of the text you see on the left side. And it's not only text, it's the same with images. You can do that. You can do exactly the same. So if you have an image like that, on the right side, you can see the vector representation of that same image. And right now we are in a state or in a phase where we're trying to vectorize everything. So from audio to animations to 3D models, we're exploring and trying to find ways to vectorize everything and anything that we have digitized over the years. And how do we do that? Through machine learning, of course. And notably so-called embedding models. Maybe who has heard of embedding models? Great. So, well, if you've played with ChatGPT or the OpenAI APIs, you would have noticed that they had so-called embedding model endpoints. And these embedding models are vectorization techniques where you basically supply a text or an image or something, and you get a vector representation back. And these have been trained over the years. There are a lot of vectorization techniques out there. The first one was Word2Vec, released in 2012 or 13 by Google. And basically, what it did is grab a word or a sentence, and it created a vector representation out of it. So there was a machine learning module that was trained to do exactly that. But it had a big problem. It didn't understand context. So a word with multiple meanings always had the same vector representation in its embedding. Now, a couple of years ago, so-called transformer models, most notably BERT, and afterwards the OpenAI CLIP, became popular, and those transformer models were machine learning applications that actually understood context. So words with different meanings in different contexts actually had different vector representations. And that was really the breakthrough that also allowed large language models to become, usable. Because you could create vectorizations of, or that are context sensitive. Unfortunately, embedding models are quite complex. So we're going to do something that I really love doing. We're going to treat them as a black box for today. So we'll be putting text and images in vectorization models or embedding models, and we'll be getting vectors out, and that's it, because I just don't have enough time to explain everything in 50 minutes. So those are vectors. Now, vector databases. Who knows what a database is? I saw something. Do I really need to show my hand for this? So vector databases. What are they? They are purpose-built databases. They have only one purpose, and that purpose is to store your vectors. Don't use them as a time series database. Don't use them as event stores. Definitely don't use them as relational databases. They have one purpose, and that is to store vectors. They are optimized to store high and index high-dimensional vectors. So they can go up to thousands of dimensions, your vectors, and these databases will be able to retrieve or to find your vectors within milliseconds. And they do that using so-called nearest neighbor algorithms, or NNS, and which these are and how they work we'll get into in a little bit. And of course, you can store metadata associated to your objects, which is really necessary if you try to build an application. You need more than just the vector of an object. You also need some metadata, right? So, so that is what vector databases are. If, for example, somebody came to you, which is a little bit tech illiterate, and asked you, hey, I keep hearing about this vector database thing. It's new and cool. What is it? I would probably give this as an answer, that it's a database that facilitates effortless and swift semantic search on your data. And semantic being really the keyword here, because if you had just search, you would probably use Elastic or something like that, or make your own solution. But if you need a semantic search agent on your data, then you use vector databases, because that is actually what they're pretty much built to do. Now, they're used quite exclusively in AI applications right now. Most notably, ChatGPT, but all AI applications probably have a vector database somewhere in their chain, but themselves are not AI. There's no AI or machine learned within the database. It is actually just an application with highly advanced algorithms, indexing and retrieval algorithms to get your data. So that means that you don't necessarily have to use them to build an semantic search on your data or something AI. You can, for example, use them, I don't know, to store your Minecraft procedural world in them or something like that. If you want to do some indexing, there are a lot of algorithms out there. Maybe you recognize a couple. So on the exact side, we have linear search, which is exactly what you think it is. Every time a vector enters the database, it will check it against all the other vectors in the database and index it accordingly. As you can guess, that maybe doesn't scale very, very well. K nearest neighbors is, of course, something that we've heard over the years a couple times. Personal favorite, approximate nearest neighbors, oh yeah. Shout out to Spotify for just naming the algorithms like that. And hierarchical navigable small worlds, which is a very interesting way to index this. It's okay. All right. And whenever you do searches, you need something called a distance metric, because when you search for a vector in your database, basically what the database is going to do is going to check the distance between your search vector, and all the vectors that are stored in the database. And then can be from Euclidean distance to Hamming distance, dot product. Maybe you heard a couple of these things. And there are many, many more, by the way. If you're seeing distance/similarity, it sounds the same, but it isn't. If you're checking for distance, basically you're asking, okay, how far away are these objects to each other? And if you're asking for similarity or checking for similarity, you're asking how close are these two objects to each other. Now, I know this still sounds the same, but basically when a distance is 0, two objects are very close to each other, and when a similarity is 1, two objects are very close to each other. So it's inverted, pretty much. Distance calculations and indexing always happen in the same so-called vector space, which is, if you think like Postgres relational database, it's a table, but we call it vector space, because it just sounds cooler, right? And they do that, you can define that by schema or by table, by object, and many, many more. Every database has its own way of defining your vector space. And basically they do that to enforce that you use the same, or you check with the same dimensionality against objects. So if you have a vector representation that has 512 dimensions, should always be checked against objects that have 512 or 384. Mathematically, it is possible to do the calculations with different dimensionalities, but it's not very accurate. Your results are not going to be very good. Now, if I hear vector space, I'm like, hey, I can do something cool with that. So that is what I did, hopefully. So these are all my data sets, and I tried to recreate vector space, the vector space of those data sets. So what you're going to see is a planet. At least I hope you guys see that this is supposed to be a planet, which represents an object that is called Longbow in the database. Now, if we fly a little bit further, anybody played Starfield, by the way? No one? Oh, poor Bethesda. All right. So if we fly, you see more objects. And what's cool is once you have numbers, you can do a lot of cool stuff. So for example, the textures here are generated from the vector representation of the object. So it's always the same texture on every planet, so you can kind of a little bit see what the vector representation is. Now, I shall admit, this is maybe not the best way to look at your data, or the most user-friendly way. I wish it was, but it isn't. But if you look at these data points, for example, here, let me make this a little bit bigger. All right. So this is our whole, all the objects in the database right now. And you can see that there are clusters being formed. For example, here we have something called Excalibur, and here we have a Morning Star, and here we have an Astra, which is quite further away, by the way, I just noticed. And here in Odachi, and this clusters is actually exactly what you want, which means the embedding model actually grabbed your objects and vectorized them in a way where things that are similar end up close to each other in your database, in your vector space. That means if I were to search for a melee weapon, for some reason, spoiler alert, it will end somewhere here close and will give me something back that is very similar to one of these data points. All right. So there are a lot of vector databases out there right now. It is a gold rush. I'm not kidding. If you every week, if you go to GitHub and search for vector databases, there are at least 2 or 3 new that have popped up in every language. So we have, if you ask which one does OpenAI use, as far as I know, they use Pinecone. There's an extension for Postgres called PG Vector that you can use. There's an extension for Redis that you can use. The other day I found out there's an extension for Neo4j, a graph database, which you can use as a vector database, which is kind of interesting business choice, but you know, gold rush. So if you really want an open source database, everything to the right is open source. You can just find them on GitHub. Pinecone is the one that I found that is completely closed. Redis, the vector module is part of Redis Stack, which is closed source. Elastic, I'll be honest, I don't know. If you look on their website, it's like, yeah, we are open, but we are not open source. I'm like, what does that mean? But yeah, so I don't know. Some databases offer so-called built-in embeddings. That means that the database will vectorize your data as you insert them in the database. And if they don't have built-in embeddings, like the databases on your left side, that means that you first have to do a call to OpenAI or Hugging Face or something else to retrieve your vectors, to vectorize your data, and then you can store the vectors in the database. Of course, if you're open source, you need to make money somehow. So a lot of them have managed services. If you really like that, PG Vector has a Supabase managed service that you can use. And of course, if you want to do some queries on your database, first things first, all of them have a Python client because Python is the AI language, right? But you can also use, for example, a REST API on the databases to call and retrieve or insert objects. Some have a JavaScript client or a CLI. Some you can just query using SQL, like, well, Postgres and TextAI. And Vespa, you can query using YQL, which I think stands for Yahoo Querying Language. I'm not sure, which is an interesting choice, I guess. Not the one I would have made, probably. So yeah, but if you want to work with vector databases, think what your requirements are and just pick one, because they all pretty much do exactly the same. They will all tell you that they are the fastest. They will all tell you that they are the best. But in the end, they pretty much do exactly the same. And unless you are really on ChatGPT scale, I don't think it really matters which database you pick. All right. So let's start implementing our own search, right? So the cool part, timekeeping, okay. All right, so for our stack, I use Weaviate for the persistence. I have a Spring Kotlin backend because Kotlin is the better JVM language, changed my mind. And, and for a front end, we use Unity. Who here knows Unity? Okay, who here knows Unity because they fucked up a month ago? Okay, not a lot of people, so that's great. So yeah, they're a little bit of popular boy right now. I made the demos before they decided to go suicidal with their business. So, all right, so why did I choose for Weaviate? It's open source, so that's great. I could actually go into the source, which actually needed to happen a couple of times. It can be run completely modular. The documentation is actually pretty decent. The client is pretty decent, though it's a lot of generated stuff. But, and I'm very happy it passed me because of this choice, it can run completely offline. And I don't know how your internet has been today here at the conference. Yeah, so I was really happy that I could just run all my demos completely offline today. All right, so when it comes to architecture, this is a little bit it. I think it's pretty simple. Any architects here? Great. So we have a front end through REST. We talk to our Spring backend, and then the Weaviate client library is in there, which will basically do REST calls or GraphQL calls to a Docker instance that runs Weaviate. Now, maybe some of you are thinking right now, okay, why don't you just go from your front end to Weaviate directly if you can just call it through REST? Well, I am a backend developer, and adding abstraction layers is basically my job, so that is what I did. For today, we'll be using cosine distance as our distance metric, hierarchical navigable small worlds as our indexing algorithm. We'll have a BERT model for our text vectorization, a ResNet 50 model for our image vectorization, and CLIP model for when we're going to do same space vectorization. What that exactly entails, you'll see in a little bit. So for the mathematicians here, if you are the cosine distance, this is basically the formula for it. But I think what you're most interested in is that if it's your distance is 0.0, that means two vectors are identical. And if it comes out 2.0, that means that two vectors are opposite to each other. So that means basically if you have a Java class and you vectorize the whole Java class, and you have a C# class and you vectorize the whole Java C# class, it will come out as close to 0, right? Because C# stole everything for Java. That is what I've been hearing. And if you have a JavaScript file, I guess. And then the Java class, they will probably come pretty close to, well, far away from each other, I would say. So that is basically, so the smaller the number, the closer the vectors. And then we have hierarchical navigable small worlds. This is a little bit trickier to explain, so I hope, yeah, that's tricky indeed. All right. So let's say these are all the objects that we want to be putting in our database. Once we start putting, inserting objects in the database, one by one, for every single object that is inserted in the database, it will do a proximity search and find an X amount of closest objects. In our case, 3. So it will search for the 3 closest objects that it can find. So as you can see, inserting is pretty slow, right? If you have to do a proximity search every time you insert something, that takes time. And basically, at some point, as you can see, you are building a graph in your index, or a neighbor graph, or whatever you want to call it. Funny story, this looked a lot like a pentagram the first time I ran it. So I had to remove actually a couple of data points. Not trying to send subliminal messages or something, you know. At some point, there's like a 1 in 3 chance that a data point is going to be duplicated in your index, in the database. And for the duplicated points, they were going to be duplicated into a higher layer, so to say, and exactly the same thing will happen. So the proximity happens on a second layer. And then eventually, in our case, it's going to go all the way up also to a third layer. So you have 3 graphs layered on top of each other, the one more complex than the other. And a couple points are duplicated in in your database. So there are like in your index. So there is some duplication in there. Then if you do a search, and let's say the search is here somewhere, that means that this is the object. This is the object that you want to find. The database will start searching from the same entry point always. It's always the same on the topmost layer. And then it's going to try and find the closest vector to your search. And then once it found that on the topmost layer, it will go and use that as an entry point in the second layer and go from there. And then again, we'll do that on the bottom layer and go from there. And as you can see, you're skipping a lot of complexity and a lot of steps by doing it like this. And algorithms like that is what allows vector databases to retrieve objects extremely fast. So let's add everything we have left, all our data points, clean up a bit, and then we'll do another search over here. And then as you can see, exactly the same. It's the same entry point and searches for the closest vector on the top layer, and then again on the middle layer, and then all the way down to the most complex bottom layer, which otherwise would have taken quite some time. And yeah, that is really nice. It's a really nice approach to solve a problem of scale. And like this, vector databases can basically search through millions and millions of data points in a database and within milliseconds and give you the best result, or what they think is the best result. We'll get that. We'll get to that later. Who knows what this is? I'm so proud that people actually realize what this is. Yes, this is the Matrix. There's a scene in the Matrix where Neo is asking for a lot of guns. But there's a flaw in this scene. And the flaw is that he has no way to search for the guns, so we're going to help him. So we have a small CSV file. And these are basically the 3 properties of our weapons. So the name, the type, and the range. So for example, Excalibur, the type is short and the range is short. And then once we insert this in the database, basically it removes the property names. You can choose to keep the property names, but here we choose to remove them. It will lowercase everything, and you're going to get weapon, Excalibur, short, sword. And that string is going to go through a BERT model. And it's going to be vectorized, as you see down there, and it's going to have 384 dimensions. Not a lot. So, of course, the more dimensions you have, the more accurate your search becomes, but it also becomes slower. So there's like a fine dance between speed and performance and speed, well, a lot of times. All right, if we look at our data, it is actually pretty, so this is basically all our data. So it's not a lot, it's just a word here and a word there. It's pretty simple. All right. This is just like the movie, right? Oh, why are you laughing? All right, so Trinity is asking us, trying to talk us out of it. And we're like, no, 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 we're going to save Morpheus. He's the coolest. And then we're going to search for weapons. Anybody that has something that I would like to search? An AK-47. I got you. I also play Call of Duty. All right. The texture is missing, unfortunately. But there you go. So you found an AK-47. If we look at the distance was 0.22 between what we search and this. But this is not really a semantic query, right? This is more like an exact search. How about a Japanese sword? It is a sword, but it's not a Japanese sword. So what if we do a Japanese weapon? An odachi. And that is a Japanese weapon. There we go. So, and this is really a semantic search, right? So I haven't said anywhere that something is a Japanese weapon or sword or whatever. The vectorization model just basically puts them close to each other. That, okay, an odachi is actually a Japanese weapon, so this ends up pretty close. But as you could see, it's not 100% accurate. So the first query was like a Japanese sword, okay, and I got a scimitar, which is not really, it's more Persian, I think. And that is kind of the beauty of vector databases, if you ask me. You never know what you're getting out of it, given. So, but given a query, you're always sure to get the same result back. So a query will always give you back the same result, but you never know what the result is. And you know, what's life without a little bit of gambling? But yeah, this is a quite simple example. We can go a little bit more sophisticated. Do we have anybody that plays Dungeons and Dragons here? Okay, good enough. So Dungeons and Dragons, a very popular role-playing game. So on Kaggle.com, there are a lot of open source data sets. If you need a data set, Kaggle.com. That is where I found all the spells in Dungeons and Dragons, and I put them in the database. I'll show you in a little bit. We have a wizard. He's a little bit forgetful, so he's strolling through the forest, and at some point he's going to be ambushed by a thug, and then we're going to help the wizard come up with spells in Dungeons and Dragons to cast against the thug and defeat him. That's going to happen through a BERT model, so our text is going to go through a BERT model, and hopefully we can find something to help this poor forgetful wizard. If you look at the spells, this is a little bit more than what you just saw, right? So this is a lot of text of all the spells that are in Dungeons and Dragons right now. Castable, every class, etc., etc. And what I did to actually make this quite semantically queryable, so to say, I had to create a very semantic description for the spell. So the CSV is like very computer readable. But I made a description that is more human readable. Did you have a question? Oh, so as you can, hey, this spell can be casted by these classes. It has this level. It has this casting time, etc., etc. And adding things like that really makes your data queryable in a semantic way. So it's not like, okay, I'll just grab this unstructured data I have and just put in a vector database and problem solve. No, I think there's a lot of times there's going to be a little bit of structuring or creating nice paragraphs around your data. And then what I did is basically I told the database, I don't want you to vectorize all these properties like the classes and the range and the material cost, etc., etc. I only want you to vectorize the name of the spell and the description I just created, and that's it. And that means the vector representation is going to be only of those two properties. But once you find the object, you can get back all the properties, which is necessarily for if you want to do things with your in computer, right? All right. So anybody that played Baldur's Gate 3? A couple more people. Huh? That shows what the better game was between that and Starfield. All right. Anybody that wants to try something? A magic bolt? Let's see what we get. Oh, how about a magic bolt? We get guiding bolt, cordon of arrows, and chain lightning. Was that what you were searching for? So, and then we can cast guiding bolt and. So, as you can see here, magic bolt. Is that a spell? What is it called exactly? Well, we're at 5 now, man. How about something explosive? Or explosive. Speak with plants, plant growth, and entangle. Does explosive mean something in different language? So we're gonna. Yes, everything does the same. So, if we do something explosive instead, a fireball, and an ice knife. So it gets a little bit closer. So I'll cast the fireball. There we go. So as you can see, it's exactly what I said. You are not sure what you're getting out of the database, which you need to be prepared for, of course, if you use these things. So basically, you're building your data set, and what comes out always has to be somewhat okay or right or whatever. All right. But we can make it better, and I'll show you in a little bit. All right. But before we go further, you can, of course, also vectorize images. Anybody that has played Pokemon Snap? Did you like the game? No, yes, okay. So it's a game where you just are on rails and you're taking pictures of Pokemon, and it has sold very well for some reason. So we're gonna have Ash that's gonna find Pokemon. He's gonna flip his hat because that's what he does, and then we're gonna take a picture of, and hopefully we'll find the correct Pokemon. Do we have any Pokemon? Sorry, but do we have any Pokemon masters here? People that are like, yeah, I really know Pokemon. So if I ask, hey, in the Poke Index, what is Pokemon number 1? Who can answer me? Bulbasaur? That is true. What if I say number 25? Pikachu? Who said Pikachu? Oh, it's oh my God. Yes, it's true. Again, number 25. Or how about 15? PG? No, it's Beedrill. Oh man, pretty close. All right. Well, actually, once I did the same, and there was a guy, he could just, up to 200, could name them all. It's insane. Anyway, so this is Ash, as you can see, exactly like the Nintendo games. What is this Pokemon? Mario. Yeah. Same company, different. All right, so let's take a picture. And so what we did underwater is we took actually a picture of what the camera is seeing. We we encoded it to base64. We sent it to the database, and we're like, okay, give us back whatever you see, whatever matches this the closest. And if we take a look at and the distance was 0.29 from each other. So it was pretty close. I'll show you the icons of the Pokemon I have in a little bit. Of the mushroom? Are you trying to break my demo? All right, picture of the mushroom. Well, to be honest, the ears, it is pretty close.
What was the distance?
The distance was 0.32. Now I'll follow with my demo if it's okay. Which one is this? Beedrill. Zelda. No, it's Galad. So, so let's try it again. Now it's Beedrill. So as you can see, it's not completely foolproof. I'll do one more. Should be here somewhere. Which one is this one? Wrong. It's Drifloon. And if you look at the distances, it's like, oh, pretty sure, yeah, 0.3, yeah, should be fine. If you take a look at what I did to make this work somewhat, this is what the camera is seeing. It is not seeing the mushrooms or the world. It's only seeing Pokemon and yellow. Now you're like, hey, you mother, you're lying to us. Well, that is because if you look at the icons, not these icons, the Pokemon, there we go. So this is the icons I put in the database pretty much. So this is, well, number 1, Bulbasaur, of course. Number 5, Pikachu. Number 37, then you're like, yeah, I'm no Pokemon master, but anyway. So you see, they're all a very cartoony picture of a Pokemon with white background. That means anything that was nearly, because the vectorization module did not understand Pokemon, it was not like, yeah, this is a Pokemon. So it kind of defaulted to colors and poses. So that means poses that were close to each other would be found. Well, now I have a 3D model that I'm trying to match against a 2D model, which is very tricky. There's two different things. So if I really want to make this foolproof, I would have probably need to invest a couple millions to train my own model to understand what a Pokemon is, if it's not out there already, or maybe just use more pictures, more of Pokemon. So different poses of 3D models, you know, stuff like that. Make it easier for the database to find a matching image to the Pokemon. So what I did is, I basically, to make sure Pikachu can be found, is I made the camera always see yellow on the background. So that means the color would match to Pikachu, always pretty much. And then when the contour, and I made sure that Pikachu was always a little bit lower, so I could see his face very well. And that would mean that, you know, the face has quite distinct features, so that would match Pikachu also very well. It's a little bit of demo magic. Sorry?
Can you debug this? If it says the wrong Pokemon, can you debug why it says the wrong Pokemon?
You can go pretty far, so you can print out the distance and what the distance was between the two, and all kinds of things. But the biggest problem lies within the embedding module, not necessarily the vector database.
So when you pictured the mushroom, we just had a yellow picture without...
Now, I'm pretty sure it saw one of the other Pokemon I've in the scene in the background. All right. Our wizard is forgetful, so he went back. But this time we're going to make things a little bit more Baldur's Gate-y, so to say. He's going to walk around. Again, we're going to help him cast spells. But this time we're going to grab the spell we found, and we're going to grab the name of that spell and put it back in the database to find an icon that matches that spell. Yeah, a little bit more flair. All right, great. So if you look at these, the icons I have, where am I? There we go. All right. So these are basically the icons I put in the database. Just like that. No other data was. So I just grabbed it as it was, and I put it in the database. No labeling, nothing. So I just went through the vectorization model, the clip model. So here you have a wolf. Here you have someone screaming hard. Here you have a trap, I think a spider. I bought these icons like 10 years ago from a Humble Bundle. And finally, I got them to use them for something, so that was fun. So yeah, so they are basically even the name, as you can see, is just icon and number. So nothing that would show me that this is a purple lightning or magic-y thing. All right. All right. So we are here again. I have an explosion quota. In all my sessions, I need to show an explosion. So we're going to start with that. And I'm pretty sure nobody can really argue that, for example, fireball, it is an icon of a fireball, right? So what happened here is we did a search on our spell database as the second, as we had on the second demo. We found fireball from something explosive. We grabbed the fireball name of the spell, and we queried our icon vector space to see, okay, give me something that looks like a fireball. And as you can see, that is, I think, pretty good. And this time, when we cast it, explosion. Anyone has any wishes? Magic missile, that was it, right? Magic missile. An arrow is a missile. Bam. Have we cast this? Fireworks. Pretty close. Someone said, I wanna turn him into a frog. Frog. There we go. Alter self. True polymorph. I mean, that is pretty good, right? And even so if I grab this one, let's see what we're gonna get for, again, the fireworks. Now, if we have colors, and you can work with colors, what I did is I extract the average color out of an icon, and I match a particle effect to that color. So let's say if we, for example, want to do something icy, something ice. Investiture of ice or ice frost. Okay, let's go with this one. You can see it's a blue particle effect. And this is, and like this, you can actually query things in the same vector space as text and images. If we look at the distances, oh, maybe I shouldn't have printed the whole base 64 image. There we go. You can see the distance between the text and the image was 0.69. By the way, I have a filter on 0.9, so if the distance is above 0.9, I won't show it. That way you actually don't, it's possible for you not to get results. Otherwise, it will always find something, I promise you. The vector databases are really passionate about finding you something. Here again, 0.6954. So as you can see, these distances are a little bit further from each other. And then, how about the strongest spell in Dungeons & Dragons? Wish. And there you have Wish or Ceremony or Beacon of Hope, which I think the icons are pretty fitting to what we actually are doing and casting. All right, so Wish. Again, I think, oh, nice. And how about a last one, something poison us? Good enough. The good thing about vector data, you can make typos. Nobody cares. All right, protection for poison, detect poison, disease, and contagion. Let's go with detect poison, which should be mostly green. There we go. There. Dead. Great. All right, enough playing. Let's continue. Yeah, so that is done through so-called, so not every embedding module can do this, vectorized in the same space. If you want to do that, you can use the OpenAI clip model, which you can just download off Hugging Face if you need it. And those are trained to actually put text and images in the same space. And I'm pretty sure soon enough you'll see models popping up which can put text, images, and audio in the same space, or animations, or 3D models, and you name it. All right. Who here likes coffee? And the chairs are pretty good, so maybe coffee. Anyway, who sees this and is like, yeah, I know what this is? Oh, there's a lot of people. Yeah? Yes, this is Death Clock Metalocalypse. I'm a little bit of a metalhead myself. Well, and with a little bit, I mean a lot. And I have this problem. When I hear, a good metal song with a lot of grunting, I'm like, oh, what are they saying? I can't understand. And then I thought maybe with the power of AI, I can solve this issue. I can put up my phone and be like, okay, listen to the music and tell me what these lyrics are. So that is what I try to make. So what we're going to do is I downloaded Whisper from OpenAI. And it's a transcribing model. So it grabs a piece of audio and tries to transcribe whatever it hears in that piece of audio. And I have in the database, I have all kinds of songs with lyrics. So we have songs from Beyonce, Billie Eilish. I don't know if there are Billie Eilish fans here. Ed Sheeran, Coldplay. And I have 3 metal songs. Enter Sandman by Metallica, Through the Fire and the Flames by Dragon Force, and the Duncan Hill's Coffee Jingle, which is the international coffee anthem, of course, as everybody, of course, knows, right? By Death Clock. All right. So, on the left side, you can see the lyrics that are transcribed, what the AI thinks is being said right now. On the right side, you're going to see what the actual lyrics are of the song. On the top, we'll be querying the database live, like every half a second or something like that, with the lyrics we're hearing right now, and see if we can find exactly the song that we're searching for. Anybody who thinks here that easy will find this immediately? Oh, really? Who thinks no way, Jose? who thinks maybe sometimes? Okay. Well, place your bets. So it's transcribing right now. If you don't like metal music, I'm sorry. You'll have to. It's only 1 second. 1 minute. Sorry. Beyonce. There we are. A little bit. Nice. Lady Gaga. Taylor Swift. Pretty close. Selena Gomez. Dragon Force. At least we're in the correct genre. Coldplay. Beyonce again. Body Heat, Selena Gomez again, and Beyonce. Maybe they should think about going into metal or something. Post Malone. Again, Selena Gomez. And then the solo is also transcribed to you for some reason. And as you could see, it was only a fraction of a second that we got the correct song, I think, which actually is the first time that it found the correct song after doing this for a couple of times, even for a little bit. So that is basically all. So what I have to say is, if Skynet actually rises and the robots start coming after us, I think if we just start grunting to each other, then it's gonna be fine. They'll just have no idea what's happening. They're like, coffee? Are they talking about coffee? What is this? So thank you very much for watching. I've 20 seconds for questions. I think I can take one question, and that was it. Thank you.